We are going to cover some chapter 5 today, mostly stereochemistry. And my hope is to kind of set you guys off on a kind of a thought process to mull over on spring break about the three-dimensional structures, especially of tetrahedral carbon atoms. So before I get to that, I want to go ahead and make a couple of announcements. First of all, I've adjusted the deadline for the Achieve homework number 4 to be this evening at 9:00 p.m. A couple of you expressed, reminded me that we had not covered the reactive intermediates prior to the original deadline of homework number 4. So I just basically adjusted that so that if there were any of you that were waiting until we saw it in class on Wednesday to be able to do that homework, you won't get a late penalty for that. So also, if you just forgot about chapter 4 homework in general, you got a grace period here. So make sure to get that done before 9:00 tonight. I've opened up a homework for chapter 5. We'll get a good start on chapter 5 today. And then the first part of the week after spring break, we'll go through the rest of chapter 5. So right now it's going to be due on Friday morning of the week after spring break at 9 a.m. So you'll have that whole week when you come back to work on that homework. The last announcement, as you guys hopefully all saw from my Canvas announcement that got pushed to everybody yesterday, I have decided to reopen quiz number 3 as a booster for everyone. This is designed to kind of compensate for concerns that folks had about some weird technical glitches. And also there were a few folks who said they didn't know about the quiz. As a reminder, everyone, I know it's an online course, but it is still a course for 3 credits at a university that's, the 3rd ranked research university in the state of Virginia. So we really do need to treat it like a course. And that means that you guys are responsible for knowing what you missed if you have to miss a class. So I don't take attendance in the traditional way of taking attendance. I do have the participation portion of your grade is designed to kind of capture if you're keeping up with the course and give you some credit for staying with me as I go through the material. But it is up to you to review slides that I post after the class if you're unable to make it to class or touch base with a friend or what have you. So also as a reminder, on the syllabus, I can give pop quizzes. So I don't usually do this, but it is allowed and it is valid within the syllabus. I have said that I will not always announce the quizzes. So far, I've always announced the quizzes. My plan right now is to keep announcing the quizzes, but that is really my prerogative. And also per your syllabus, there are no makeup quizzes. There are no makeup exams. So you can check your syllabus for the details related to that. But in a class this large, it is literally impossible for me to do makeup assessments because it would delay when I could release the grades and the material to the rest of the class. So there are no makeup quizzes or exams. For the quizzes, I do drop the lowest. And for exams, if you have a legitimate university recognized reason to have missed the exam, then your final exam grade can be used to replace your exam grade. All of that's in your syllabus, so you can check it out there. Regarding this quiz number 3 booster, it is open until the end of the evening tonight, 11:59 p.m. You can use your book, you can use your notes, you can use the internet, you can use any resources you want as long as it's not each other or another human being. But the real goal here is learning. The real goal here is to have you guys understanding and learning. And so please take your time as you go through this quiz. And if you're unsure of your answer, go look it up and check your answer. You don't have to take it like a quiz. It's open until 11:59 p.m. and there is no time limit. No time limit. Okay? Okay, so please take advantage of this. It's really designed to help you guys both in learning and in your scores. Okay, now on to stereochemistry. So today I've got just a couple of topics pulled out of chapter 5 to talk to you about today. We started in on this a little bit on Wednesday to kind of give you guys a flavor, and we'll build on what we talked about on Wednesday, and then we'll learn also some terminology and nomenclature related to chirality and enantiomers. So let's get started. The first couple of slides are actually going to be a review of what we did on Wednesday at the tail end, because I got the sense people were a little distracted with the quiz coming up. Okay, so first of all, I want to remind everybody about isomerism, what we learned in chapter 1, that isomers is the term that we give molecules that have the same molecular formula but are not the same molecule. So anytime we have isomers, we are going to we have to, by definition, have the same overall molecular formula. But if we have two compounds that are isomers of each other, that means that we can't do any rotation or flipping things around to convert one to the other. The only way to convert one to the other would be to actually rip some bonds apart and move things around and put them back together. So just as a reminder, if there is free rotation, if you can rotate to get from one to another, those are not isomers. So these two compounds that I've drawn out here are not isomers of each other. They are the same molecule, right? You can rotate around this center bond here, and you can see then that they would become identical to one another. Okay, we talked about from chapter 1, two different versions of isomers, two broad categories of isomers. The first was constitutional or structural isomers, which have different essentially backbones or scaffolds, right? So they would have differing arrangements of the branching patterns. They would be different. We also talked about stereoisomers, which by definition are two isomers that differ only in the arrangement of the atoms in space. So what I mean by that as being different than the backbone or scaffold is that you could switch just two bonds on the same atom and you would have stereoisomers of each other. So in chapter 1, we learned about cis and trans stereoisomers, and we applied these both to pi bonds, cis pi bonds and trans pi bonds. We also applied them to rings, whether the two substituents are pointed on the same side of the ring, which was cis, or on the opposite side, which is trans. And in chapter 5, we're going to learn about actually many new kinds of stereoisomers, but for the pre-spring break period, we're going to limit ourselves to just one, and those are called enantiomers. Okay, enantiomers by definition are non-superimposable mirror images. So they are mirror images of each other, but you cannot overlay one with the other. And don't worry about the second bullet for now. We will get to chirality in the next couple of slides. So here's an example. This is the same example I believe I showed you just at the end, just before the quiz on Wednesday. If you look at this molecule and this molecule, you can see that they are mirror images of each other. If we put up a mirror on one and draw the mirror image, it would be over here. You can see this bromine is coming forward in both cases. That hydrogen is going back in both cases. Both we have a methyl group going up and we have an ethyl group going kind of out to the sides. So these are mirror images of each other. If I were to pick up this molecule on the right and try to set it down on the molecule on the left and try to overlap things. So imagine if I rotate around this bond here so I can move the ethyl group around to the side so it lines up with the ethyl group here. When I do that, the bromine will have to swing around also, and the bromine will end up in the back. This hydrogen will swing around and it'll end up in the front over here. So you cannot, it's impossible without breaking bonds, you cannot pick up this molecule and overlay it perfectly on this molecule. So these two compounds are enantiomers of each other. That is their relationship. So if I say, what is the relationship between these two compounds? You could say these are enantiomers. Okay. In terms of using the word chirality and chiral, chiral is a term that can apply both to a specific location within a molecule, as in a chiral center or a chiral atom within a molecule. It can also apply to the overall molecule, and they have slightly different meanings, but you'll see how close they are and how much they make sense. Let me back up and just make sure we've got this concept down. Enantiomers, by definition, are two compounds that are mirror images of each other, but that cannot be overlaid with each other. So by definition, they are non-superimposable mirror images. So if you have the mirror image and you pick it up and you try to twist it around to overlay, say, this carbon chain, then the other two substituents would not overlay with each other. They would be reversed. So these two compounds are enantiomers of each other. The word chirality also relates to enantiomers. And actually, let me go back and say, every molecule that is chiral must have an enantiomer. If you have a molecule that's chiral, then there exists a mirror image of that molecule that does not superimpose on it. So the next question is, what is chirality? What do we mean by chirality? So chirality is, one way of defining it is a handedness. So my two hands are mirror images of each other for the most part, but they cannot be overlaid, right? They have my four fingers. If I overlay my four fingers, my thumbs would stick out on either side. If I tried to overlay them so I have all four fingers and my thumbs, then they're not really overlaid perfectly, because in one case my palm is facing towards me, and my other case my palm is facing away. So that's the same reason that your right hand glove does not fit comfortably on your left hand, and vice versa. So there's a handedness to your hands. There's also a handedness to some molecules. And those molecules that have this handedness are called chiral. If it can be only one hand or the other, it is called chiral. A molecule or an object that is achiral will be a case where you have a mirror image that you could then pick up and overlay perfectly on the original. So the chair here in this picture on the right is achiral because there's no distinguishing feature sticking off to one side or the other. So when we put a mirror up and we draw out the mirror image of the chair, we can pick up that mirror image and it's identical to the original object, right? The same is not true for hands or some molecules, because if I take this left hand and I try to overlay it on the right hand, I can't do it. They're not identical. Here are some other examples of things, objects, that at first glance might look like they're achiral, might look like you can superimpose the mirror image, but when you look closely, you actually cannot. So every object on this page is chiral. So if we look closely, at the top, we have the mirror image of a car, and at first, it kind of looks like it can be superimposed, right? It has four wheels, it's got two headlights. But then we realize, well, besides everything under the hood, the steering wheel is on one side in one car, and it's on the other side in the other car. So these two cars are mirror images of each other, and they are not identical, which means these two cars are enantiomers of each other. And this car is chiral, and this car is chiral. Same thing with the screw here. The threads on the screw become reversed when we make the mirror image. So our two screws are not identical. They're different screws, right? They wouldn't fit into the same pre-drilled screw hole if it was threaded. And same thing with these scissors. Of course, if we pick it up and try to overlay it, then the side with the larger handle hole would be on the back if we tried to pick this up and overlay it with the other one. This is the same thing as like righty and lefty scissors from when you're in elementary school and doing arts and crafts with glue and construction paper. Okay, so all three of these, again, are examples of chiral objects because the mirror image does not match up perfectly with the original object. All right, so here we're back to our enantiomer example, so back into molecule land. And I've said that any molecule is chiral must have an enantiomer. So we've talked about chiral molecules where the overall molecule is a not superimposable mirror image. But I also want to point out that we can talk about chiral centers, because the reason in this case for this particular molecule, the reason that this works is because this carbon is attached to four different things. And if you have a tetrahedron that has four different things attached, then there's exactly two ways to orient them. There's exactly two ways to arrange them, and they're not the same as each other. So someone's asked in the chat box, is a molecule that is an enantiomer the same as a molecule that is chiral? So there are some subtle distinctions here, and so I want to hold off on answering that question directly, because if you have a molecule that is chiral, then somewhere out there an enantiomer exists for it. But it doesn't have to be. So when we talk about enantiomers, we're talking about the relationship between two defined molecules, right? The same way I could ask you, what's the relationship between a cis and a trans pi bond? And you would tell me that they're geometric isomers. Enantiomers is a type of relationship between two molecules. You don't need two molecules to tell me whether or not a molecule is chiral. And we'll see some examples. I know that might have been confusing. Trust me, as we get through more slides, this will become a little bit more clear. Okay, so how do we know if a molecule is chiral, right? So let's break that down. Let's look at just the atom involved in creating that chirality to the molecule, right? We can have, I told you the word chiral can apply to an overall molecule, or it can apply to an atom within a molecule. So if we're talking about an atom within a molecule, we can call these chiral carbon atoms. We can also call them asymmetric carbon atoms. Those two words are interchangeable. These chiral carbon atoms, like I was saying just a moment ago, when you have a tetrahedral center, so any sp3 hybridized center, if there are 4 different things attached to it, then there are exactly 2 ways to orient those things around that tetrahedron. You can't get from one of these to the other by rotating. You would have to pop off some of these atoms and move them around and exchange the atoms, right? And there's no rotation that can get me from one of these to the other. So anytime you have a tetrahedral center, such as a carbon atom that's sp3 hybridized, that's bonded to 4 different groups, then you have a chiral center. All right. Anytime that you have a tetrahedral carbon atom, or it can be other atoms too, but every time you have a tetrahedral center where the 4 things bonded to that tetrahedral center are different from each other, that center is chiral. The mirror image is going to have a different configuration. And usually, not always, but usually, this chiral center existing will make the overall molecule chiral. We'll talk about the exceptions to that because there are many exceptions to that. But usually, if you have a chiral center in a molecule, it lends chirality to the overall molecule, as we saw in our example here, right? In our example here, we have one chiral center right here in the center of this molecule, and that creates a situation where the overall molecule has these non-superimposable mirror images. Okay, can a carbon atom, or any atom, can a tetrahedral atom be chiral if 2 of the 4 groups attached to it are the same? You should get my hint here that if it has to have 4 different groups in my like bold and underlined and different color, it has to have 4 different groups. If you have 2 groups that are the same, then what happens is you can draw the mirror image of it, but then you can pick up this mirror image, you can rotate the mirror image around 180 degrees, rotating around this carbon to number 1 bond. And when you set it back down, it will be identical to the first structure. So I know that we're online and this isn't as cool as it could be in person, but I made a model. Oh man, my blurry background means it's going to be hard to see. So in my model, I have 2 compounds that each have 2 white atoms here, and then a green and a red. So I can hold them up so you guys can see, hopefully, that they are mirror images of each other, right? The greens are pointing towards the center, the reds are pointing outside, and the white pairs are pointing kind of down. So these 2 are not chiral centers, and in fact, they're the same atom, the same molecule, the same molecule because I can take one of these and rotate it around 180 degrees, and then it's identical to the other one. My reds match up, my greens match up, and my whites match up. So this might be a little bit hard to see if you have, especially if you have me minimized. It's a tiny little square on your screen instead of a big square on your screen. But build your own model kit and convince yourself. If you have two of the same atom off of a carbon, there's no way for that carbon to be chiral. If, on the other hand, you have four different things, so now I've got a white, a purple, a green, and a red, and I'm going to hold them like this so you guys can see their mirror images of each other. I've got reds coming to the inside now. These are purple in real life on my screen. They look blue. Blue headed to the outside. There's greens in the back. And so these are mirror images of each other. When I try to overlay these, I can overlay any 3 out of the 5 atoms. So hard to do. Okay. I don't know if you guys, my hands are in the way. I've overlaid the white, black, and green atoms on this side, so you can see that. I promise I'm not gonna change the overlay. I'm just gonna turn this around so now you can see that the red and what's purple in real life but might look blue on your screen are not overlaid. So these are mirror images of each other that are not superimposable. So these two molecules are enantiomers. They're also, each of these has a chiral center in it, because that chiral center has 4 different things attached, and that makes this molecule overall a chiral molecule. Okay, someone's asked, can we not rotate? You can rotate as much as you want, but it doesn't matter. There is literally no rotation that can help you to overlay these things, because it doesn't matter. Anytime you line up 3 of these things, the other remaining 2 will not line up. And so build yourself a model kit. If you didn't buy a model kit, that's okay. If you have toothpicks and marshmallows and can label your marshmallows, you can do this too. If you have toothpicks and gumdrops that are different colors, you can use that too. Okay, somebody asked a question in the chat, but I can't see it because it's too narrow. Would any molecule that has a tetrahedral carbon center bonded to 4 different things be entirely chiral then? Okay, this is where we get into some subtleties. Usually, if there's a chiral center in a molecule, that makes the overall molecule chiral. However, there are exceptions to this, and there's actually kind of a lot of exceptions to this. So we'll see some examples that will help make things clear. One thing I can say is that if a molecule only has 1 chiral center in it, then that molecule will be overall chiral. Brittany, do you have a question?
Yes, I was wondering if on the quiz or exams, if we would be able to use our model kits as a reference.
Nope. No. Part of this class is learning how to visualize these things based on the paper version, and having to learn how to either see it in your head space or draw it out in a different way. So you can draw, like we do here, you can draw what it looks like after you make the mirror image, or down here, draw what it looks like after it's rotated. But part of learning organic chemistry is being able to visualize those things without having to build a model kit. So I totally 100% encourage everybody to build models as you're studying and as you're getting to know these different stereoisomer names and such. But when it comes for assessments and exams and stuff like that, you cannot use your model kits. And if you're ever in doubt about that, imagine what it would be like in a classroom taking a test and everybody's building their model kits and holding up their things and going like this. So, you know, that's that skill set of having to figure out what it looks like on paper and visualize it either in your head or drawing it out in a different way on paper that makes sense to you. That's part of the learning outcomes for this course. Okay, so we've talked about how chiral centers, we've talked about tetrahedral carbon atoms as being chiral centers. And indeed, carbon is the most common one that we're going to see, but like I said, it can be any atom at the center of a tetrahedron that has 4 different things attached. And I'll show you an example of that on the next slide. This gets to the question that we were just talking about. Most of the time, having a chiral center will make the overall molecule chiral, but there are exceptions to this. So if you're ever not sure, you can draw out the mirror image and see if that mirror image is superimposable or not superimposable, and that'll give you your answer. Chiral centers themselves are a subset of a bigger group of atoms called stereocenters. And stereocenter literally just means any atom where if you were to break 2 of the bonds and put them back in the opposite order, you would get a new compound or a stereoisomer. So we'll see some examples of all of these things in the next couple of slides. This is just a bullet that says 2 types of stereocenters, but it'll be better in the pictures that are coming up. So let's do the pictures. Okay, so here I've said already that chiral centers are going to be any tetrahedral atom bonded to 4 different things. So it's not limited to carbon. This is the same example that we had on that first slide today. It can also be, for example, a nitrogen atom that happens to be bonded to 4 things if those 4 things are different. So notice here we have an N-propyl group, an ethyl group, an isopropyl group, and a methyl group. So 4 different things in this case. These chiral centers are designated by a little asterisk or a little star. That is a common designation that organic chemists use, and it's one that you guys will need to use. So if you have a chiral center, you can mark it with this little asterisk. That doesn't mean you have to mark every chiral center all the time with an asterisk, the way you have to put in formal charges when formal charges exist. But if I say label the chiral centers in the molecule, that's the labeling that you should use. Or if you see this little asterisk as you're looking at a molecule, that should indicate to you quickly and easily that that carbon or whatever atom it is attached to 4 different things. Okay, so these chiral centers, as I said, are one type of stereocenter. So I'm going to show you the other type of stereocenter now, and that is a cis-trans sort of a situation, whether it's a pi bond or a ring. So stereocenters are going to be any 2 locations, any atoms in a molecule, where if you take 2 of the things that are attached to it and rip those things off, break the bonds, and put them back in the opposite order, you get a new molecule, right? So if I take off this methyl and this hydrogen group and I put them back in the opposite order, we get a totally different molecule. It's a trans double bond instead of a cis double bond. Likewise, if I take off this bromine and this hydrogen and I put them back in opposite places, I have a whole new molecule, right? We've already tried to superimpose those 2 molecules and they're not superimposable. Okay, so.
I'm sorry, I had a question. If you do that for stereo centers, if you pull them apart, you'll always get enantiomers?
Nope. For chiral centers, if you were to pull 2 pieces off and put them back in the opposite place, then you would get enantiomers for chiral centers. But there's other kinds of stereocenters like cis-trans double bonds or cis-trans around a ring system. If you pull off 2 of those substituents and put them back in the opposite order, what you would get are cis-trans isomers, or another word for that is geometric isomers. So they're not enantiomers of each other because by definition, an enantiomer is a mirror image of something that's not superimposable. And if we draw out what we would get, so on the right here is the line angle drawing of what's drawn, and on the left is the line angle drawing of what happens if we swap that hydrogen and that methyl group. And so you can see, looking at these 2, they are not mirror images, so they can't be enantiomers. In order to be enantiomers, they have to be mirror images and they have to be not superimposable. But these 2 are cis-trans isomers or geometric isomers, either term is fine. And that means that this carbon, where we did that swap, that carbon is a stereocenter. Just like each of these chiral centers is also a stereocenter. Did that help answer your question?
Yeah, I think so. So if I move those, I'll get geometric isomers. Is that all the time or just for this example?
It depends on what we're talking about, right? So if we're talking about the cis and trans type isomers, which are geometric isomers, then when you swap these two, you would get geometric isomers. If we're talking about chiral centers, then when you swap these two, you would get enantiomers. I think as we move through this chapter, later on in the chapter, after I've introduced some more types of stereochemical relationships, there will be kind of a flow chart that puts everything into categories together, and I think that'll nail this down for you. So I'm going to move on for right now. That flow chart is also in your textbook, so if you're confused about this in the meantime, you can go find that flow chart in your textbook. Okay, so if we have a situation, so we've already talked about how if we have a chiral center, then all 4 of the substituents have to be different. If we have 2 that are the same, these are going to be the same structure. So we've already seen this picture before. But it turns out another way of thinking about this is that if you have a compound where you can make the mirror image and then rotate whatever you need to rotate, either the whole molecule or bonds within the molecule, and overlay it with the original, that overall compound is achiral. When the mirror images overlap or are superimposable, that compound overall is achiral. And an easier way, because sometimes it's hard to rotate and see all of the different 3-dimensional movements that could happen without breaking bonds. And that's a key part here. We're not breaking any bonds when we do this. Sometimes it's easier to look for a plane of symmetry. So this is the same molecule we had before. And if we kind of shift it around a little bit, so instead of looking at it like this, where atoms 1 and 3 are in the plane of the screen and 3 and 2 are going forwards and backwards respectively, we can take the same molecule and just shift it a little bit. So both of the atoms labeled 3 are coming towards you and the 1 and the 2 are going back. And hopefully you can see at that point that this molecule rather, has a plane of symmetry right down the middle of it, right? So you can make your own model for this and try to see it for yourself. When you have a plane of symmetry within a molecule like this, that is another indication that a molecule is achiral. So what that means is that, and this should be intuitive to you, there's a mirror image within the molecule. So if you were to put a mirror up here and draw out the overall mirror image of the whole molecule, because of this internal symmetry, the mirror image of the whole molecule would be the same as the original. So therefore, they would be superimposable and they are achiral. Does that make sense? Okay. So this gets back to the question that keeps coming up. This aspect, this internal symmetry, means that there are occasions where you can have a compound that has 2 chiral centers in it, but if they're located in just the right place on either side of this internal mirror plane, they could actually essentially kind of cancel each other out if they're mirror images within the molecule, and the overall molecule would be achiral. So I can show you some examples of that I think will help make it easier to see. Here is a cyclopentane that has 2 chlorine substituents that are cis to each other. When we have this orientation, you can draw a mirror plane of symmetry right down the middle of this molecule. And so that should tip you off that this molecule is achiral. The other way, if we couldn't visualize that mirror plane, the other thing to do is literally draw out the mirror image. And when I draw out the mirror image, of course, there's also hydrogens up here. It doesn't look exactly the same because my art with my mouse is not as good as, graphic design art. But this is the mirror image as if it was an external mirror. But you can see we can pick up this molecule and it overlays perfectly with that one. So both methods are going to get us to the same answer, that cis 1,2-dichlorocyclopentane is achiral. It does not have an enantiomer because when you draw out the mirror image can be superimposed, achiral. If we had the trans version of 1,2-dichlorocyclopentane, so we have the same cyclopentane ring, but now our two chlorine substituents are across the ring from each other or trans to each other, this compound no longer has a plane of symmetry. And that means that when we draw out the overall mirror image, this mirror image does not overlap with the original. There's no way we can pick this up, flip it over, turn it around, rotate it. There's no kind of rotation or movement in space that we could do to this molecule to get it to overlay with this molecule. We would have to break bonds on this one to get it to look like this one. So these two versions that are both trans 1,2-dichlorocyclopentane, these are enantiomers of each other. Okay. This also is just a reminder of the definition of enantiomers. So these are mirror images that are not superimposable. All right, so just a reminder kind of where we've come from and where we're headed. This is the same isomers overview slide that I gave you in the beginning. And just a reminder, we can break isomers as a whole group down into two categories that are constitutional or stereoisomers. Those are two different categories. And then within the stereoisomer category, so far we know our cis-trans isomers from chapter 1, and now we know enantiomers from this chapter. So why do we care? Who cares about stereochemistry? Why does it matter? So I have two geometric isomers up here. Hopefully you guys can see that these are a trans and a cis isomer. And if you think about it, this whole pi system, all of these atoms that I'm running my laser pointer over have p orbitals. It turns out that they are all lined up. So this molecule is entirely planar. All of these sp2 hybridized centers are lined up with all their unhybridized p orbitals lined up. Same thing here, except it's kind of a U shape instead of a weird S shape. So these molecules have totally different shapes. So even though they are isomers with the same molecular formula, one of these is an essential metabolite that is present in your body and part of many, many, many biochemical pathways going on in your body right now. The other one, the cis version of the same molecular formula, is a toxic irritant. And if you have too much of it, it can do damage to you. So these are cis and trans isomers. It's a little bit easier to see here because the shapes are so very different, right? But what about these two molecules down here, which are enantiomers of each other? You can see that there is one chiral center in this molecule here, and the same chiral center here, but the opposite configuration is over here. So in this case, we didn't draw our mirror here. Our mirror is kind of like in the plane of the slide, right? So if you moved one of these to be back behind the other one, you would imagine that being your mirror. You can see the shape of these molecules is different too. They have the same shape and structure on this kind of left side or the core of it. But then there's this big bulky group that in one molecule sticks out towards you and the other molecule sticks back behind the screen. So these molecules, both of them are called carvone. That's the kind of the common name for them. You don't need to remember that. But it turns out that the orientation around this one carbon, that's the only thing that's different, is the orientation around this one carbon. And because of that, the one on the left smells like spearmint. The one on the right smells like rye bread. Isn't that neat? This is like organic chemistry at work here. So we have spearmint smelling compound on the left, rye bread smelling compound on the right, and the only difference, they have the same molecular formula. They have the same carbon scaffold in terms of where, like, how many atoms of one type are connected to atoms of another type. The only thing that's different is how those atoms are connected in space, where this group either is coming forward or going back. And that small difference means that it interacts with your receptors in your nose very differently to send a signal to your brain that is very different as well. Okay, so I told you both of these molecules are called carbone. So that actually brings us into our next topic here, which is that we as chemists, we have all these IUPAC rules for nomenclature so that we can name things in ways that are not ambiguous. But I just told you both of these molecules are called carbone, right? So if I said, oh, hey, can you go get me the jar of carbone off the shelf? How do you know if I want the one that smells like spearmint or the one that smells like rye bread? So in order to handle that, what chemists have done is come up with a set of rules to name the different configurations at any chiral center. So for the rest of the time today, I'm going to introduce this concept to you guys. We're not going to make it to DNL isomers today, but I'll get a good start on these Kahn, Ingold, Prelog rules, which are named after these three old guys who came up with this priority scheme. Okay. So here are two enantiomers of each other. Here is alanine and a different version of alanine. So alanine is a common amino acid found in many of your proteins. And the one on the left is the version that's found in your proteins. There's a chiral center here that has 4 different things attached to it. And you can see that on the right, we have the opposite configuration there. So if I were to use IUPAC nomenclature, both of these compounds would be called 2-amino-propanoic acid. So I recognize you guys haven't learned that type of nomenclature yet, but you'll just have to take my word for it. They would both get the name 2-amino-propanoic acid. So we need a way to differentiate them and to name them in a way that makes sense to all chemists everywhere. So what we're going to do is look at the rules of how we go about doing this. And that's this Kahn, Ingold, Prelog naming convention. Sometimes you'll see people call this CIP or SIP. I didn't learn it that way, so I usually don't use it that way, but I think it happens in the book sometimes. All right, so anytime you have a chiral center, whether it's a carbon or whatever, there's, by definition, it's going to be a tetrahedral center that has 4 different things attached to it, right? There are exactly 2 different configurations that those 4 things could be attached, right? And we saw that with the model systems that we had here. There's only 2 ways that you can arrange 4 things around a tetrahedral center. So what we can do is figure out a way to give a designation to one configuration or the other configuration based on its 3-dimensional orientation in space. The first thing that we have to do is assign priority to the 4 different substituents. So they're always going to have 4 substituents because by definition, we're talking about tetrahedral centers, and they're always going to be different. So we will always be able to assign a priority scheme to them. The ones with the higher atomic numbers get the higher priority. So you can look at a periodic table or whatever you need to do, but you can assign priority based on the atomic number. One of the caveats of that, one thing that means that if you have isotopes like a carbon-13, that extra neutron in the carbon-13 will put it just ahead of regular old carbon-12. Likewise, if you have deuterium, which is sometimes labeled like that, but also sometimes labeled with a D for deuterium, which is a hydrogen atom that has an extra neutron, so it's a proton and a neutron. That proton plus neutron, or deuterium, outranks a proton by itself, or a regular hydrogen atom. Okay, so here's an example. We are going to put our atoms in order of priority, with the biggest atomic number being first, that's the fluorine in this case. Our smallest atomic number being last, that's the hydrogen, gets a number 4. Number 4 will almost always be hydrogen, but it doesn't have to be. If you didn't have a hydrogen in your tetrahedral center, then number 4 could be something else. And then with our remaining 2, nitrogen has a higher atomic number than carbon, so nitrogen gets to be number 2. So here's our priority scheme. So that's the first step, step 1, and we are done with step 1. In step 2, what we need to do is rotate or visualize or look at our molecule in whatever way we need to look at it so that our lowest priority group, number 4, is in the back. So if our molecule is not already drawn with it in the back, one thing we can do is redraw it so that it ends up in the back. So what I'm doing here is rotating around this carbon to atom 1 bond, where I'm shifting this number 4 to the back. When I do that, this 3 will shift around to be front and left, and this 2 will shift forward to be front and right. After you have number 4 in the back, you don't have to worry about it anymore. You can ignore it. Once it's in the back and you're ignoring it, then what you want to do is draw an arrow from your highest priority, number 1, to number 2, to number 3. And if that arrow goes in a clockwise direction, you have the R enantiomer. Let's see what it looks like in the other direction. If you have the S enantiomer, so here you can imagine this is the mirror image of the original drawn right here and then put down here. So in this case, we would rotate it the other way to put number 4 in the back. When we do that, 3 will come around to be front and to the right, and 2 will come forward to be front and to the left. And then once number 4 is in the back and we ignore it, and we draw our arrow from 1 to 2 to 3, now our arrow is going counterclockwise and we have the S enantiomer. Okay, so this, these are the key steps of assigning a Kahn-Ingold-Prelog designation, which is an R or an S designation, to chiral centers. So again, this works for any and every chiral center, whether it's a carbon or a nitrogen, whatever it is in that center. If it's got 4 different things attached, you can set a priority for those 4 things, and then you can put the lowest priority in the back, and then you can draw a circle in order around the priorities that are left. And if that circle is clockwise, you have R. If it's counterclockwise, you have S. So I only have 2 more minutes. So after spring break, we'll spend a lot more time talking about what if it's not so easy to see the priorities for 1 through 4. And I think that's actually going to come up in the next example that I have. But we'll talk more about these subtleties after spring break. But here is an example of assigning Kahn-Ingold-Prelog rules. So we've assigned the priorities here. Number 1 and number 4 were easy to assign because oxygen is the highest atomic number out of the 4 things attached to this carbon, and hydrogen is the lowest. But the remaining 2 are both carbon atoms. So what we have to do from there is keep moving out away from our chiral center until we have a tiebreaker. So we have a carbon and a carbon atom. So the question is, they're both attached to this chiral center. What else are they attached to? And over here, it's attached to a hydrogen-hydrogen carbon. Over here, it's also attached to a hydrogen-hydrogen carbon. So we have to go out further. What is that next carbon attached to? Over here, it's attached to hydrogen-hydrogen. Over here, however, now we've got a tiebreaker because this one is attached to hydrogen-hydrogen carbon. And so the fact that this carbon out here exists means that this side is the priority. And so it's going to get number 2. Now that it has number 2, we can rotate. In this case, we're rotating around this bond to get number 4 to go to the back, right? And when we do that, OH comes down, the ethyl group goes up, and we have a configuration that looks like this. Our hydrogen is in the back. And now we can draw our circle around from 1 to 2 to 3, and we see that we're going clockwise. Okay, so I see I'm done with time for today, but I see some questions in the chat box, so I'll stick around and I'll answer those questions. But that's as far as I'm going to go today. If you guys need to step out and head out, then please have a safe and happy and fun spring break. I'll see you when you get back. And now for the questions that are coming in the chat box in order. First, if you have a molecular group as one of the things attached to the tetrahedral, would you look at the highest atomic number in that group? And the answer to that, which we'll go into this in more detail after the break, is no, not exactly. You have to go out systematically from that chiral center until the first time that you break that tie. So you do still use the atomic number to break the tie, but it's not whichever group has the biggest atomic number. It's where the closest highest atomic number is to that central asymmetric carbon or whatever. Hopefully that answered your question. Next question. So more carbons wins or vice versa. No, it is not necessarily more carbons, right? So I could have, if I had a group here, let me get my pen. If I had, instead of a CH2, CH3, if I had, let's see how to do this. This is a really hard example for me to do. Okay, if I had some, yeah, I can't draw this on the fly. Basically, if it branches earlier and closer to that chiral center, then it would take priority, even if overall that side did not have as many carbons. So let me just do it a completely different way. Okay. If we look at this example that I just drew up at the top, we still have a highest priority oxygen and a lowest priority hydrogen. And then if we look at the two that are remaining, they're both carbon atoms here and here. So we need a tiebreaker. And the tiebreaker is that this carbon atom on the left is bonded to a carbon and then two hydrogens that I'm not showing here. Whereas this carbon on the right is bonded to a carbon hydrogen. So because this carbon on the right is bonded to two carbons, this one now is the higher priority and this one is the lower priority, even though this group has more carbons in it. So it's not a question of more or less carbons. It's not a question of which side has the higher atomic number. It's a question of, as you go systematically out from the chiral center, what do you run into first? And you keep going and only until you break the tie. As soon as you break the tie, you stop. Okay, next question in order in the chat box says, would we be able to do the canceling of the CH2 and the CH3 and see that we have more CH3? I'm not sure exactly what you mean. So if you are still here and want to speak up and try to ask that in a different way, that would be great.
Sorry. So what I was thinking was, like, you know how CH2 cancels out with the other CH2 on the other side, and then CH3 cancels out with the other CH3, and we have a remaining of CH2. Would that still be bigger in atoms than the since we canceled everything out on the other side?
I think that what you're saying will work. Let me get rid of that and let me get my pen back. So what you're saying is that we can, I don't know why it does that. Okay, so we can cancel out that CH2 and this 2, and then we have a CH3 and over here a CH2, so a CH3 would win. That definitely works in this case. I'm trying to think, there might be cases where it's a little bit more complex than that, and it won't be quite so easy to visualize the canceling out. I think it should work, but I see it.
Okay, that's fine. Thank you, though.
So I'll get into this more after spring break, but another way to do it is to draw yourself a little map that looks like this. So whichever the carbon is that you're talking about, it has, there's one on each side. And so if you can draw out like this, there's a tiebreaker here already because there's a carbon atom here, whereas down here there's 3 hydrogens. If it's also a carbon atom, then you would have to keep going and look at each of the 3 things that those were attached to.
Oh, that works too. Yeah, I see.
So it's kind of, it's a little bit situationally dependent how easy or hard it is to see and visualize how to do the priorities.
Thank you.
Yep, you're welcome. All right, guys, don't forget to do your booster. Have a great spring break. I will see you when you get back. And take care.